Okay, great. Yeah, I was here 3 years ago to talk about what Podium is doing with geothermal and specifically focusing on the project 575 Princess, which if you're in Kingston, you would have seen it. It's been under construction for the last 3 years. We just finished it off, which is really exciting. And that was Podium's first step at taking on geothermal, trying to understand geothermal and really seeing what we wanted to do with it or where we would see it go. So today's presentation is going to be, oops, wrong screen, sorry. Today's presentation is going to be a bit of an update from the last time. So for anyone that was here 3 years ago to listen in, you'll get a little bit of a refresh because we're going to go over just the general basics of geothermal, how it works, why it works, a couple of insights that we picked up along the way working on new projects. We'll go through the design and install. So when I last spoke, we did a very specific method of install. And since then, Podium has continued to install geothermal at 4 other buildings. We've actually installed it and it's provisioned for in another 3. So in total, that'll be 7 buildings since our last visit that we've implemented geothermal. And we've done something a little different on each one for various reasons. So that'll be some experience. Yeah. It might be hidden because I'm sharing my screen. Yeah. Sorry, yeah, and then we'll talk a little bit about the operation side. So the 575 Princess just opened up fully this past month. So we've got a little bit of information on there. And then I know this group really likes to have discussion and have questions. So I'm hoping to get through the content as quickly as possible so we can really just focus on what you guys want to talk about and any questions that you guys might have. Okay, so like was mentioned, Podium Developments has been around for 20 years, and we essentially started geothermal work 5 years ago with 575 Princess. Since then, 6 more projects are under development with wellness and low carbon focus in mind. Of the total Podium portfolio, 7 projects are now either have been designed or are under construction with geothermal. And 5 of those have also gone so far as to pursue CAGBC's zero carbon building design certification. So we do have 1 building that is actually certified. It's across the street from 575 Princess. That is, I believe, Kingston's first zero carbon design certified residential building, which is exciting both for Kingston and a great milestone for Podium. And we have 4 others that are in the midst of the certification project. So Podium has really seen the benefit for both just the environment, the call to climate action, as well as what investors and end users are looking for in terms of building. So that's why we've really made a focus of on the onset of every project saying, can we make GeoExchange work for this building? And as we go through the slides, we'll see that there's a lot of factors and considerations that need to come into play with that. But it is basically the first question that we ask when we're looking at a site and trying to understand how the development of that site will proceed. So we definitely are interested in lowering our carbon footprint. We also want to become industry's leaders in producing this type of building. So people will say, hey, Podium, they're producing low carbon, efficient buildings, and that we feel comfortable doing it because it's a business at the end of the day. So the more comfortable we are doing it, the more efficient we are doing it, the better we can do it, the more we can do it, and the better it is for investors and everyone that's like pitching into the project. It's also aligning us with what investor expectations are. We're seeing more and more that pension funds and investors are looking to make sure that the product that they are investing in has this sustainability or low carbon element. I will say some investors are a little more savvy than others. Some are looking to check a box to make sure that their portfolio requirements are met, but others are asking a bit more deeper questions of what are you actually doing? What is this just a superficial exercise or does this have meaning for what you're doing? And so it's great that in our interest of becoming industry leaders, we can speak to that and we can say why we're making the choices that we're making and maybe not going in another direction with other things. We're also finding that end users are becoming a little more savvy in terms of what the expectations are. And really, we want to provide a standout product in the market. So that's why we have been focusing on trying to make geothermal or geo-exchange work at every project we do. Okay, so we're going to just jump in through the basics of how geothermal works. This may be repetitive or a repeat for some, but hopefully it'll just be a refresh and trying to put everything into simple terms, because really, fundamentally, the system and the concept of the system is really simple. There's a few scientific engineering parts in it, but the base concept is really simple. So essentially, the very first part is in the ground, we have a series of geothermal wells. So it is just a big loop that goes deep down into the ground, anywhere from 400 to 800 feet in this climate zone. It really depends on the geology and the geography and what you're dealing with. But in this area, that tends to be about the depth that we're going. All of those loops, oops, sorry, I shifted something there. All of those loops are then connected at the top by what we refer to as the laterals, and they're connected by what we refer to as headers. So essentially, every pipe will have an inlet and an outlet, and the fluid that's flowing through the pipes will all go in the same direction, up and down in this continuous loop until it's connected to the base building, where there will be a series of pumps, heat exchangers, and those systems in the building will then push the fluid through to a loop that's running through the building. So the reason why there are heat exchangers in the basement of the building where we're going from the ground loop to the building loop is that the ground loop, we typically put something like a glycol into the loop to make sure that the fluid doesn't freeze. The ground temperature, when you get deep enough, it basically equilibrates. So it's not such a concern about freezing at depths, but in that first few meters, where it's more susceptible to the exterior air temperature, there could be some risk of freezing. So we want to make sure that we don't have any slush or anything that would impact the performance of the fluid. So that then has a glycol in the fluid, and the glycol is typically not a fluid that we want to have running through the building because the heat pumps in the units don't use glycol. There are units that do, which we'll talk about a little later, but essentially that's why there is a heat exchanger down at the bottom of the building. The building loop then is connected to the individual units that are in each either residential unit or space. So these could be heat pumps, these could be fan coils, these could be VRFs. It really depends on the overall design of the building, but the idea is that the supply water is coming in, or the supply fluid is coming in at one temperature. The heat from that fluid is either extracted, or the heat from that air or from that room is either put back into the fluid, and then it goes back down into the ground loop where it cycles through and switches over. And it's just essentially running through that cycle again and again and again. So trying to put it into simple visual visuals. Okay, great. You can see the cursor. So basic winter operation is, like we said, the ground temperature throughout the year when you get to depths of 800 feet, it's fairly consistent. It's not freezing, it's not crazy hot. It equilibrates to a constant temperature. So what's happening in the winter time is that the fluid that is going down into the loop through the inlet is colder than that ground temperature. And by the time the fluid travels all the way down the loop and then back up, and then because it's all a continuous loop, it goes down the next one and then back up, and it keeps going down and up and down and up until it gets back to the building. It basically pulls heat from that ground and then raises the overall temperature of the loop, so that when it goes back into the building, that temperature is now warmer. The temperature in that fluid is now warmer than it was when it was leaving the building. So that gives some energy, and that gives some heat that the heat pumps in the units or the VRFs or whatever mechanical device is using to extract the heat can then push it out into the space. And that's how we feel it. And that's what's happening with the simple loop. There is a bit of like mechanical equipment required to either under compression or refrigeration and all the things that happen to actually extract the heat from that. It will then loop back down, because once you've pulled the heat out of the fluid to warm the space, the fluid is then cold again. and then it goes back down into the loop and back down into the ground and then heats back up, and it keeps cycling and cycling and cycling and cycling. So over the span of the heating season, what that does is you've essentially extracted heat from the ground. So if I go back up a slide, your ground temperature, when it was, say it was 10 degrees at that depth, at the end of the winter, at the end of the heating season, you would have lowered the ground temperature because you've taken the heat out of the ground and you've pushed it into the units. And if you were only ever doing that, you would run into a problem because all of the equipment that's used to make this work, they need the temperature of the fluid in the loop to be within a certain range. And so if you're constantly reducing the temperature of the ground, the temperature in that fluid then will over time eventually fall out of that range, and then you'll have a problem. That's why it's really important to make sure that we balance the geothermal system so that whatever heat you've extracted from the ground in the winter, you're putting back in the summertime. And so in the summertime, the operation is essentially flipped. So what you're doing is we think of air conditioning as like blowing cold air into a space. But for this purpose, and maybe more accurate, is what we're actually doing is taking heat out of the space. We're not blowing cold, we're taking heat out of the space. And so when we take the heat out of the space, we're putting it into that liquid because again, it's just basically going in the reverse path of what it did initially. So that heat is coming out of the space, it's going into the liquid, and because the loop is going in the same direction the whole way through, now that liquid that goes into the ground is warmer than the ground temperature. So it goes through the ground temperature and then it will disperse back into the ground. And then what you'll end up is that your earth temperature that was colder will now raise back up by the end of the summer. And the whole process with the design where you're considering how big your field is, how deep it is, how many HVAC units you have, all the various components that you're thinking in the design are all trying to balance that the amount of heat that's taken from the ground in the winter with the amount of heat that's put back in at the end of the summer. And the idea is that over the course of a year, you end up with a nice balanced system. So you take the heat out and you put it back in, and you take the heat out and you put it back in. And that would be a perfect balanced system. But in reality, the systems are never 100% perfectly balanced, mainly because if you think about where we live, we spend a lot more time heating than we do cooling our spaces. And so just intuitively, you're like, oh, well, we're heating more. We're going to overall, over the course of the year, be taking more heat from the ground. So how do we mitigate against that? And how do we make sure that we're still balanced at the end of every year? Because when you hear about people having issues with geothermal systems, it's mainly because they haven't maintained that balancing over time. So maybe one year you're monitoring the temperature of your loop, you're monitoring the temperature that the water's going in and coming out of, and you see you've lost a couple degrees, and maybe you had like an exceptionally warm summer, or maybe you had an exceptionally cold winter, and those might cause shifts in the temperature on a year-to-year basis. But if you're not correcting within the next year and you kind of let it slide for multiple years, and then all of a sudden nobody's been paying attention, nobody's been doing anything, and now your ground temperature is outside of the range that works for your mechanical equipment, that's when people talk about geothermal failure and having issues. But if you're paying attention and you have included in the design mechanisms in which you can balance and recalibrate, in theory, the system can run in perpetuity. That's what's the beauty of geothermal and the simplicity of it. So how do you balance it? And what are the design considerations that you need to think of when you're working through what is this design going to be? So the very, very first one is understanding what the soil composition is of your site. So we've got soil. Kingston is actually a great example. We've got soil that maybe runs somewhere between 3 to 12, about 12 feet, 3 meters. That's what we encountered at 575 Princess. When we got to the 3 meter mark, we were starting to hit bedrock. Bedrock is great for geothermal. So Kingston is in a great position to really utilize it because of the conductivity of the rock. Essentially, it has a high heat capacity, it has a high conductivity, so the efficiency of transferring the heat from the earth to the fluid is really good. In soil, where you might not hit bedrock or something until you get much further, like 400 feet or something, you don't have as great of conductivity. You need a lot more length of pipe in order to generate or pull the same amount of energy from the earth. And so really understanding your composition will help define how big of a field do you need. Like in theory, you can just dig to Middle Earth, but practicality says like that's not realistic. That's not something that builders want to do. That's not something that anybody really wants to do. So it may be feasible, but the practical side has to come into play of like, what can you actually do? The downside for Kingston with the bedrock is that your bedrock is also very hard. Like we found with the other projects that we've done, this has been the hardest earth to drill into. I know, and I apologize for any of the neighbors at 575. It was a noisy period and a long period of drilling, and I was on the phone with the neighbors, and I could hear it in the background, and my heart went out for them. Because I couldn't do anything about it, but it was very difficult, and the contractors were constantly saying, we're going through drill bits like you wouldn't believe, and they all underbid the job because they didn't actually expect it to be so hard, and they had to fly in new bits from Alberta and get specialty rig people to come in, and it was challenging. Thankfully, we didn't have to go as deep because of the efficiency and the effectiveness of the soil. So that's definitely something to factor in, and I know it comes into play when you're actually costing this system for your building. Is how much is it actually going to cost to put in, and how easy it is to drill and how easy it is to get those wells in the ground is probably the biggest contributor of how much this system is going to cost. Whereas we're doing another project in Oakville, and again the bedrock there is about 9 meters, so it's a little deeper, but we were still very happy that it was relatively high. And so we told the neighbors, we're like, it's going to be the worst, like it's going to be the horrible experience because of what we had here. And this thing is like, it's like butter rock in comparison to the rock here in Kingston. And it's a mix of shale. It's come up really easily. The neighbors are like, oh, that wasn't so bad. I was like, thank you. And so it's really important to just do the the geotechnical investigation, get the boreholes, really understand and make sure that your trades are aware of what they're getting into, so that you don't have conflict later when all of a sudden they're like, this isn't what we expected. We've gone through all the bits we have in all of Ontario. What are we going to do to get this in? So subsurface conditions definitely matter. And really impact the feasibility of putting geothermal in. Also lot size, because if you're not going deep, you might be putting more wells in. And you can obviously only go within your lot boundaries. And it doesn't have to be under the building. The whole field could be outside of the building. But if you're building on a tighter lot, and going deep becomes really difficult, but you don't have the width to necessarily put in a lot of fields. When you do the cost benefit analysis of that, that can be a factor into really deciding, can we make this work on our project? I should have flipped through a couple of slides while talking about all this, but I got carried away. This is what happens when you're in person. You get to make eye contact and you forget about the slides. But essentially essentially the apologies to everyone online. Essentially the gist of the slide here is if the bedrock is up higher, if you reach bedrock sooner, you have the ability to potentially make your wells shallower. Whereas if bedrock is way deep down and the soil conditions are not so great, you will either need a lot more wells or you're going to have to go a lot deeper to get just the overall energy from the ground that you're going to need to heat the building. So we talked about Ontario being a heating dominant climate in the sense that we're heating more of the year than we are cooling. And what does that do to our geothermal field in terms of that balance that we're trying to achieve at the end of every year? So In a heating dominant climate, it becomes a little trickier to balance the field, because if you think about a cooling dominant climate first, so that's a climate where you are air conditioning more than you are heating, which means you are putting more heat into the ground than you are taking out. What that means is you have leftover heat at the end of the year. So we can find things to do with leftover heat. We can preheat water. Hang on, let me check if I have a slide about this before I keep going. We can preheat water. We can, I actually put it down here. Here, we can preheat water. We can actually heat parking garages for the shorter time in the winter. We can use it for snow melt systems anywhere there. So extra heat in a cooling dominated building can actually be put to some good. And even though Ontario in a whole is heating dominant, some of those larger towers, like condominiums or like those glass boxes, even though we're in a heating dominated climate, because of all the glass and the greenhouse effect, those buildings generally tend to be cooling dominant, because people in there find that they're so hot all the time. And also there's the efficiency of the grid of the building, where you're not on an outside wall on every face. So those would be examples of cooling dominant buildings. But in Kingston here, where we're doing more mid-rises, longer stretching buildings rather than like the tall towers, we found that we were dealing with heating dominant building. And what that meant was our cooling season, when we were trying to inject heat back into the ground to supply the next heating season, we were a little short on the balance. And how do we refine that so that we're not short on the balance? So there's a few kind of easy fixes, and there's a few more design related fixes that you can do to balance that out. So I would say the first easy fix is to just connect your loop to your domestic hot water. And basically, anytime that your field temperature is getting a little too low, you inject some hot water into it from your domestic hot water. So it's a great solution. It's on demand. It's simple. It employs practices that construction teams are generally familiar with. The downside is most domestic hot water is connected to natural gas boilers. So in terms of the carbon reduction aspect of that, doesn't really help the situation. So it's not perfect, but again, when you're looking at the metrics of your project and what you need to do, and really another question is, how often will this boiler actually come on? It's not a everyday type thing. It's more of you're monitoring your well temperature over the course of a couple of years, and you're like, hey, we need to run this boiler for 3 days to bring up the temperature, and then you turn it off again. So all of those things need to be considered and factored in when you're trying to figure out the best approach for adding heat to the loop. The other thing that needs to be considered when you're working through what the size of your field is and trying to balance things out is, what are your occupant loads and what are the assumptions? And how do the assumptions that the mechanical designers make compared to what's happening in real life? And we've found that we've had a lot of conflict on our teams with that, because good conflict, challenges. We're challenging each other. And the reason for that is the mechanical teams and the electrical teams, they need to design for absolute maximums. Like, what is the peak that this is going to see? What is the biggest number? Can we carry that? Throw a factor of safety on it and make sure that we've got this nice big number that we're ready to use. If you just take that number straight and apply it to your geothermal field and say, we're going to have all the people in the building at all the time, and all of the exhausts are going to all run at the exact same time all day, all of a sudden your field has like exploded in size. And the metrics of making it practical to install become tricky. So you have to have this discussions back and forth with your design team of, okay, are we comfortable with this assumption? Are we comfortable saying, okay, people really only run their dryer once a week, or and you kind of thread the needle and balance to try to bring those occupant assumptions down, because the occupancy assumptions will affect your air change requirements. And even though we've got ERVs in all our building, they're not 100%. They will not recover 100% of the heat that's exhausted out. So we're essentially sending our conditioned air out. So that's something that we have to recoup. That needs to get factored into the calculation of the field. So all of these things, and there on this particular item, there's definitely a lot of back and forth that goes between those two design groups. And depending on your contract structure, they might not care. They might say, sure, let's make the field as design build. We'll make the field as big as you want. But if they have more of a stake in really helping become efficient, they will challenge the designers to make sure that they're putting forward something that's really realistic and actually representative of what's going to happen in the building in real life. Another factor about the occupants of the building is, are they all there? And this might be actually something really specific for Podium. So Podium, while we have done a wide range of projects, our main focus has been student living in communities adjacent to universities, and those types of projects. And so students are usually here from September to May. And May, whether or not they've leased the space for the whole year, they may not be in their unit as much. And especially in our heating dominant climate, we're really relying on that air conditioning to go back into the building or to go back into the loop. And if they're not there, they're not running their air conditioning. And if they've gone out, that can also shift the balance of the system and make things a little wonky. And this was actually a question that our designer was like, I've never dealt with this before, where maybe 60% of the building just like says adios for the summer, and who's running these air conditioning. So implementing things like making sure that all of the thermostats in the units are actually connected to a master control that the property manager can control, to make sure that at the very minimum they're at least coming on, just to set a baseline to run something. This was another reason why for 575, the approach that we took for managing the heating dominance imbalance was we did connect the loop to a domestic hot water boiler, because we on this project actually pivoted to geothermal a little later in the design process. So there were certain things that we couldn't change. There were certain things that we couldn't do differently. And we felt that it was the best way to mitigate the risk of having to rebalance and top up the system. So just again, another thing that you need to consider of is the human factor, and how are occupants actually going to live in the space, and how you design the space will impact how occupants live in the space. So if you've got a glass box, your occupants, regardless of what climate they're in, they're going to feel probably hotter than if you've got a well-insulated, low glazing ratio building where the interior temperature of the unit might be more indicative of what's happening outside. So all these things need to be considered into your design. So you can see that it's simple system, simple approach, simple concept, but lots of things impact and change how it runs and how it operates. So building performance now is really the big ticket item. So this is, how does your building perform aside from the geothermal system? And that will really have a huge impact on what your geothermal system is. Because if you're taking care of air leakage and you're not losing this preconditioned air that we talked about, you are putting less work on your geothermal field. So you can make it a little smaller. If you are if you have well insulated walls that you're not just spitting heat out or spitting conditioned air out, again, you're going to put a little less work and effort on your geothermal system, so you can make it a little smaller. Solar gains, like, are you employing passive shading methods, or making sure that your glazing ratio isn't out to lunch, so that way people aren't overheating when they don't need to be. Again, that's on the flip side, you're reducing your cooling demand, so you can potentially make the field a little smaller. And then just the overall efficiency of the mechanical system. If your mechanical system is more efficient, with every turn of that loop, you require a little less and less and less. So that can also reduce the size. So what we found, what we're doing at, so 485 Albert, which is the one right across the street from 575 Princess, the one that has received the zero carbon certification. That project is using a VRF system, and I think it's using the 4-pipe VRF. So it is like a spider web of pipes in that building. And basically the idea is that all the units, all the mechanical units in all of the suites are all interconnected with each other before it goes into the loop. So if you've got a suite on the west side and it is getting the hot afternoon sun, and your suite on the north side is a little cooler, it's not getting sun, so this guy is heating and this guy is cooling, they will actually exchange energy between those two units before it goes down into the loop and does the mass exchange. So that will help, again, further reduce the size that you need for your geothermal field, and just the overall efficiency of the building goes way up because you're not relying on like a single source coming down. You're actually buffering everything essentially before you actually go down to the bottom. Anyone can chime in at any time. I'm just trying, there's a lot of information, so I'm just trying to like blitz through it all. Oh, okay.
I had some.
Yeah, I don't want to mess with my screen here. I'll lose everything.
While you're waiting for that, you said you could always stay within your footprint, and presumably if you go right to the edge of your lot and somebody else puts a geo exchange.
It's a question, yeah.
Is there any way you can diagonally drill? Is that allowed if you get permission from other landowners, or?
We actually asked those questions internally. We haven't gone beyond that. But the neighbor one is a big question of what happens when this becomes more prevalent and more people are doing it. And like, what if I'm taking care of my field top notch and you're a delinquent and you're not, and we're sharing that border? And all very valid questions that I have no answer to, because thankfully we haven't had to deal with it. But we are also kind of thinking ahead of, well, what happens here? And so what we're making sure we do is try to provision kind of these safety nets that we may not employ. And the main safety net is a connection to a hot water source. And so I was going to say this later, but we'll come up on it now. So basically with the, if you're familiar with the CAGBC Zero Carbon Design Certification, version 3 allows you to be certified so long as there is no natural gas associated with any space conditioning. You're allowed to have natural gas for domestic hot water, provided you have a transition plan and showing a like a cost benefit analysis as to why it makes sense to go this route. The struggle is that what we're finding is a lot of our buildings, we are commissioning or opening up for operation in a heating season where it may have not received the full injection of heat from the previous summer that the overall design was relying on. And we were like, what do? We need to boost the system before we even start. But we want to get this zero carbon certification. That's what we're striving for. We don't need it for operation. Like once it's boosted, we don't need it anymore. So really in operation, it's good, but like, how do we overcome this initial hump? And so we reached out to CAGBC and asked them, and we said, like, what do we do? Like we're having this conundrum where our system's gonna fail because we're trying to not, but really in theory, if we had this boost, everything would be fine from there. And so CAGBC was very reasonable, and they agreed that it's not part of the regular operation. It's not something that the system relies on. It's not, it could even be considered part of construction, because if you've ever gone to a construction site, they've got propane tanks, they've got like all over the place. So construction is clearly not part of the calculation. And so they said that for that initial boost, they're okay. It won't impact our certification. And we are like, great, that's amazing. And kind of the added bonus of that is because we will have needed to make that connection for the initial boost. If there's ever an emergency, we still have the connection. So the overall annual operation of the building is not intended to use it. It's the sequence of operation. It's not programmed in. It's not factored into the overall design calculations, but it is there because we needed it initially. And if for some reason, like we all know, like, it's October and it's like 20 degrees yesterday. So things are changing. We can't predict the future. We're running our models with climate data that may not be a true representation of the future. So it does give us a little bit of a safety net if we need it to boost and charge the system. So What was the actual question? We went on a, Yeah.
That's why you're dumping fuel into the ground instead of directly to the heat loop. There's an efficiency loss charged to the ground as opposed to just heating the building with a VHW.
sorry,
But you're using at 90% efficient boiler to heat the grounds,
Mhm.
and then you're pulling heat out of the ground. There's another efficiency loss. Why not just supplement the heat of the building?
Yeah, where it's connected in the loop is it's essentially all the same, because it's you're essentially doing the same thing, but ultimately the end goal is to raise the ground loop temperature. So if you're injecting it higher up into the loop so that it just goes straight into the building, when it runs back down into the ground loop, it will have gone up a little bit. So the where it's going exactly, that's up for the designers to figure out as part of the whole sequence of operations where they put it in. Essentially, because it's all a closed system, the end goal is to just get that ground temperature back up over a period of time, so that way you don't have to do it anymore. Yeah.
I think the question was that if you're doing that in August, right, you're adding that heat to the ground because you're not getting enough cooling. Why not, instead of putting it in the ground in August, just add the hot water in February when you actually need it? Because you might be losing some of that heat that goes to your neighbor's geothermal or whatever.
Yeah, I think
it's being used as a battery. Why not just use it?
I think you can use it anytime, and I think it's like
Well, in the summer you're getting it for free because it's cool and
yeah. There,
No, but adding the hot water, I think you're saying.
that's something that happens in the winter, like to make up.
you're so as part of the system, you have a team of professionals that is monitoring the well temperature, and so we're going to skip ahead, but that's okay. The on the operations side, so we're only just starting to scratch the surface of the operations of these things and all these little nuances, because we had our first batch of residents move in May, and now the building is fully occupied in September. So it's still been really early in terms of what's going on with the actual operation of the system and the monitoring of the wells. But we're really excited because this is our first one. We've got 6 more down in the pipeline, and we know that this one, we know that we're building better on other buildings, so it's really going to be exciting to see all like the metrics come in. So what we did was we employed a geothermal monitoring firm. So essentially their sole job is they've got temperature sensors on the inlet and the outlet of the well, as well as they're monitoring pump speeds, water rates, flow rates, and volumes. And they are just paying attention on an annual basis to see what's going on. And I think they're going to do it either annually or every 6 months, give us reports to say, this is what it's looking like, this is how it's tracking, this is what we think you should do. So they're going to make recommendations along of the lines of add more heat, or they're going to say run the pumps a little faster, run them a little slower. They'll make a recommendation to the building operators on what to do. But the main message that they gave us was don't touch anything. they said they made us get on a phone call with property manager, their staff, everybody, and we were like, we're great. What do we need to know about the system? They're like, don't touch anything. Just don't touch it. They're like, if you see a pump doing something different, that's fine. Just don't touch it. If you see the temperature on this gauge not looking the same as it did yesterday, don't touch it. Like that was the main message, was don't touch it, because unlike maybe conventional systems where it's an instantaneous response or an instantaneous action, this is something that they actually need to look at over the span of a little bit of time, see where it's going, see where it's trending, figure out what to do, and then make a recommendation. Because although I did talk about a geothermal system failing, and that's ultimately what we don't want, it doesn't happen tomorrow. It's a gradual thing over time that if you don't pay attention to it over time, you got a problem. But the idea is that we are going to pay attention to it on regular intervals and adjust it on regular intervals with the guidance of the team. So they will tell us whether or not we need to adjust the sequence of operations so that more heat is ejected at this time or that time, and how much and for how long. But we're trying to, because what we've heard from other operators and other installers is that when things are going wrong, or when things go wrong quickly, is usually when somebody's like, oh, I gotta make that pump go more, because it was running yesterday, so I think it should run today. And so that it's a little bit of like a habit change, because it's definitely a different system for a lot of operators who are more familiar with like the cooling towers and the chillers. And so this is a different setup, a different mindset, and a different mentality of, we don't need to necessarily instantaneously react to everything we see, but we need to assess on like a global scale of what's going on for the building.
Right, can I ask, where, in this multi-residential system you have, are you putting a heat pump in every unit, in every resident? So you basically have a background cold water or hot water loop, and then, so every unit has their own heat pump.
Every unit has their own.
And their own water to get air heat pumps.
Yes, yeah, every unit has their own heat pump. Yeah.
It may seem like a detail, but do you have closed dryers that vent outside? Or are you requiring residents to buy newer technology like the heat pump?
So we looked at the dryer. So the dryer and the venting and the whole thing is just like apart from the geothermal, it's just a whole thing that needs to be looked at. And so for this particular building, we do have the dryers that vent outside. The heat pump style that it's like a washer dryer combo all in one. They don't work the best. They're not necessarily great for like user experience. So we've shied away from them. But because of all the venting, it's like the duct work, the load it puts on the mechanical systems, the inefficiencies, and just like the space and the cost and the maintenance of the units, we're actually like moving more to common laundry rooms to help alleviate that problem, or deny a challenge, to help alleviate that challenge.
In the last year, like North American size heat pump dryers are finally, there's some reliable ones coming on the market.
Yeah.
So I can see that changing.
But then we'll add another item to our electrical load, which is then the other struggle that
but
we
they're
come
so
into.
much more efficient than
Yeah.
Oh, these
Maybe
are
one more and we'll let you get back.
Yeah, all good. You're all skipping slides for me, so it's all good.
That triggered my thought, because we have a heat pump hot water heater.
Yeah.
So, but we're off fossil fuels, so we don't have any natural gas. Have you looked at the heat pump hot water heaters?
Yep, we have. At this point, or at least when we last looked at it, financially, they were very restrictive or difficult to.
You know, my Home Depot, they're like, I don't know, 800. Yeah, 600, they're not expensive.
Yeah, but you're on a building of this scale. We're not. We're talking about like a room size unit to facilitate all those, because in the way that we designed.
They're not in the units themselves.
No. It's a building wide water system. Yeah. So the size of the unit needed to do that, and then also the demand requirements of people, the resident experience is something that we also have to factor in, and their ability to get instantaneous hot water. Google reviews matter. So we have to factor that into the design. Okay, let's see what the next slide says. Let's see. Okay,
How long do you think you have?
I'm gonna try to go quick. I can skip through the constructions part really quickly. We'll just look at some pictures, but we'll go through as quickly as we can. So another thing that has come up is we're going deeper because we either have to, because we have to build parking, which we don't want to, but municipalities are forcing it. So we're going deeper, which means we're going deeper into the water table, which means municipalities are also moving away from continuous discharge of groundwater. So we're finding we have to raft and bathtub a lot of our foundations. Geothermal typically would just penetrate through, but if you had a typical slab but now you've got this membrane that you're trying to keep perfect and basically not have any water go through it. And a question came up like, so do you penetrate the slab and waterproof it 100 times, or do you have to bring everything across and under the slab? But what happens if you need to fix a header? Are you going to ever get through 1.5 meters of concrete to fix that thing? Or are you going to, so this was a conundrum that we had of keeping the headers accessible by puncturing the raft slab and then running all the headers above the raft slab, or saying, okay, we built it, it's great, and running everything under the raft slab and penetrating at a more reasonable spot. I think the jury is still out on exactly the best approach. We've looked at both of them, and maybe in 3 years' time we can report back on another experience. But it's something that you should consider with your design teams when you're looking at this, but also asking yourself, how much do you rely, or how much do you trust the success of this geothermal system? Because one of the nerve-wracking parts about it is with conventional mechanical systems, you're installing the mechanical equipment at the very end, and then you're checking it and you're like, great, works, done, offsite. With this, you're installing this first. This is the very first thing that goes in, and you're just leaving it there. You do a pressure test in the middle, but then it's not until maybe like 2 years later that you're finally connecting everything back and running it through and seeing that it all worked. And I won't lie, that was very nerve-wracking at our first project, because it was the first time we've ever done this. Lots of stuff's going on until then, and we've got all these headers and we're making the connection and we're like, yes, there's still pressure and everything. But again, so your level of comfort in relying on the system may impact your choice on whether you want to go through or around a raft slab. And that's something to discuss with the owners and the investors and the stakeholders to see what they think makes the most sense. This is a big one that has come up since the last time I was here, and it's the available electrical service. So we're electrifying our buildings. Great. We're talking about heat pumps for water. We're getting away from natural gas. We want to put EV chargers in all the buildings, photovoltaics on the walls. All those things are great. And what we're finding is we go to the local utilities with our offer, or with our register to connect, and they look and they're like, huh, that's a big number. That's a big load. And I think also in communities, and if you're building in areas, and this was specifically an issue in Kingston, was they haven't had a lot of experience with these big multi-unit buildings with air conditioning. That was a new element that was added to their questions, and they look, they're like, that's a big number. Where are we going to get that from? And it was also an issue in Oakville, where Oakville was a completely different issue, where they actually had the service, they had the power available, but they had no substation to connect to. So they were like, it's in the road, but we don't know how you're going to get to it. And Oakville Hydro said, you know what, we can build a new substation, but we don't have any place to put it. So the city needs to approve putting this somewhere. And the city's like, well, that's ugly. We don't want it on our, I'm not, this is a conversation. And we're sitting there saying, you guys want an electrified building, you guys want low carbon, you guys want to do better, you guys want to develop in this area, in this community, and we're telling you we need to update the infrastructure, and you're saying that you just don't like how it looks on the sidewalk. Like, can't we figure out like painting it, or like putting some like trees around? And there is a disconnect between all the different parties of what they want and what they need, and where things are going. So this was a really challenge. So also the cost associated with it, because we budget our projects with the assumption that we know we have costs associated with the offer to connect, and we do our best to budget with them, but we assume that there's something to connect to. And all of a sudden you're bringing 4 kilometers of 44 kV from around the corner on poles and down, and the utility says, well, this is for your project. And you're there saying, well, it's going to benefit everybody. And so trying to work through maybe a payback structure, or yes, we'll pay for it now, but as other people connect to it, we'll get something back. There's a lot of discussions around this, and it's a serious question, because it can have really big impacts to your site plan, what you're able to do. Talk it through, make sure you understand what's available. And it is a struggle. We talked about this, about CAGBC letting us use natural gas for the boost. We'll come to the final points at the end. Again, I know some people want to see some construction photos. So I'm going to blitz through this really quickly, and then we'll pretty much have wrapped up everything. So this is an example. This is a photo of 575 Princess. There are 2 ways that you can install your geothermal field. You can either install it from the top before you start digging, or you can excavate the building and then go into the pit and install your geothermal field there. Installing from the top is considerably easier when it comes to mobilization and getting the trades on site and just access and all these things. But the reason why you might not do it, it really depends on how you're financing your geothermal field. So if you've got good funding behind you and you're able to just pay for the whole thing, install it from the top, make it easier. If you are financing through a company like a Diverso or I can't remember the other name, where they basically act like a utility, they start charging you for that field from the second their drills go on site. So if you do it from the top, you'll drill right away, but then you're going to spend a year excavating, and then they're going to come back in. So you're essentially paying for a year of financing of this geothermal field without actually getting anything. So that's why it might make more sense financially to put the field in when you're down at the bottom of the pit, so that you're trying to basically put it in at the last possible second to start the costs associated with that. But from a simplicity standpoint, and it's a lot easier if you just do it from the top. So how it works from the top, and I don't have a great photo of this, and I got upset at my teammate for not getting a better photo, but how it works from the top is essentially the drill rigs, when they go down, they know what the set elevation is of the underside of the slab. And they shove in what was described to me as foam golf balls, basically into the pipe at that location. And then they have a cutter that will cut the pipe just a bit above the height of the golf balls, and then they just abandon it. And then they pull everything out. So basically, as you excavate, once you get to the depth of your underground of your underside of your footings or underside of your foundation, you'll then all of a sudden this pipe will show up. So let's go through some of the photos here. So this is an example of 575 Princess, where you can see we had significant bedrock coming out. This was what our poor neighbors had to endure. It was a little rough. But once the rock is out and the excavation is in, this is where we got the booms in. These coils here are essentially the pipe. So the pipe comes pre-measured. So you to the supplier, you say, we need 600 foot lengths, we need 800 foot lengths. And it comes pre-measured with a pre-molded turn at the bottom. So they're not trying to bend the pipes on site, and they're not trying to like create that turn on site. And so what they do is they just feed that bottom part into the pipe, and because it's all pre-measured and they're putting the pipes at the set location, it'll stick out exactly where it needs to be. You need to make sure that you have water on site because it's drilling. Depending on the hardness, you're going to have a lot of friction there, as well as you need to manage the slurry and the slop that comes up out of the drill. That actually ended up being a whole line item in itself, because depending on the material and where it has to go and who's managing it, and the drill rig guys are like, I don't want to deal with this, and so you need to get another guy in there with a bobcat moving everything around. So it's something that wasn't necessarily factored in initially, but another line item to consider. So here's an example of what it looks like once the pipe is sticking out. Then once they fed the pipe in, they grout it with a bentonite mix. So essentially, the more wet it gets, the more it continues to cure. So that helps with the waterproofing properties of the pipe, and making sure that if there's any small punctures or issues with the pipe, the actual bentonite mix around it will continue to help make sure that we don't have a leak or any sort of pressure drop. So here you can see this is at 575 once they put all the wells in. Here's the other site where we did the connection where we did the drilling from the top. So we drilled from the top, and then they excavated down, and this is in Oakville where we've reached the shale. And what they did was, you can see these trenches, and these trenches are where the wells are located. So the flat part outside of the trenches is essentially the underside of the slab. And what I've been told is that you can see the holes. You see these 8-inch diameter holes on the top side of the slab. And so what they'll do then is where they're like, okay, there's one right here. They take a hand machine, they chip around it, they expose it. And that's what you can see these guys doing here. And I don't know if I can zoom in easily, but essentially they have found the top of the well after chipping out around it, and they're just sealing it off and making sure that everything is ready for the next stage of the connections. So once the wells are all found and identified, they put in the headers, which is this little top bent piece, and then they connect the headers to what we are calling the laterals that run along the entire base of the foundation. So that first photo was at 575. This is the one in Oakville where the laterals are running in trenches underneath the slab. These connections are all welded on site by hand. They have a device that looks essentially like a hair curler that they use to melt the PVC, and then they put a special solution on the other pipe, and then they do the male female together and hold it there for a period of time, and that's essentially it. So it's all, each connection is hand welded on the spot. Once all the connections are done, they fill it with a fluid and they pressure test it for, I think, 48 hours to check and see, to make sure that they haven't lost any pressure over time. So although ultimately all the wells are connected in a single loop, they do group them into what we call main headers. And so that way it'll be easier to identify, okay, we've got an issue with row number 1, row number 3, 4, 5, 6, 7 are fine. Okay, flipping through. So here we have the backfill going in. Everything gets consolidated into a localized point. And that's essentially the install that happens, and then the rest of the building goes in. So these are just the 7 projects that we've done geothermal on. So 575 Princess in Kingston. This is Geo Park across the street in Kingston. This is the zero carbon building certified. Down the road, actually, I think it's pretty close from here on Queen Street. We've got another project under development in Kingston. So these 3 are our Kingston gems. Over here, we've got a 13-story building in Toronto. This is our tallest, 26 stories in Scarborough. It's under construction right now. They've done all the header work and the install. So the next big milestone for this building will actually be connecting it to the main building system, which will probably happen in about a year. We've got another building coming up in Scarborough, affordable housing project. And then this is the one in Oakville. All right. And then ultimately, everything comes up into a mechanical room where the pumps, the monitors, the heat exchangers are all held. During construction, it looks like a little bit of a spiderweb's mess, but once all the pipes are wrapped and insulated, everything is white nice, and it's probably the cleanest, simplest, tidiest mechanical room you've ever seen. So like I mentioned, the main message from operations that we've received so far was don't touch anything. But I hope to come back in a couple of years, probably once we've got more buildings under our belt and some monitoring data from this project. Be great to be able to share more on that side of things. So bit of a blitz at the end. Sorry about taking so long, but
I just I can rephrase the question that was posed twice. Basically, are the does the
It was about the design considerations for horizontal.
with horizontal loops, are they equally effective or not? They say it's 4 feet.
Yeah. So the question was about horizontal loops and the effectiveness of that. I really think it depends on the soil conditions and really what temperature range you're trying to balance back and forth between. Another loop option that we didn't go into because we haven't really accounted them are open loops, or I guess they're not. It's like a non-loop where essentially you get lucky and you find like an underground water source or like an underground aquifer, or you're close enough to like the ridge of the water that you can just get that to work. That would be the ideal scenario, because then you have essentially, you're not needing to put back anything because it is constantly being refreshed and recharged just from the natural system. So it really just depends on the design parameters available. But if the soil is workable and access is good, drilling technology has come a long way. Like those guys in Alberta can drill through anything. It's just really working out what makes the most sense. And for like a single family home, we're not talking about hundreds of wells like we are for these projects. For one well would probably fit the needs of a well-designed house.
Any more questions here?
Just curious, was there considered alternative rather than U-loop, right? Something like concentric double pipe?
So that technology has come out, or at least we've been informed of that technology relatively recently. I think they're using it more in Europe. We haven't used it on a project, but we were going to look into it in uh, an upcoming one. One of the installers that we've worked with has suggested it. So the pros and cons to it, I can't speak to right now, but I have heard of it, and it was suggested by a trade relatively recently.
We have two, probably it's easier for you to read. One was, I don't know even what MECP is. How does your find the MECP approvals process?
Ministry environment.
So the MECP process, or the MECP requirement that we've had for this, was that the drillers needed to be certified and sign off that they understand all the can't think of the word, but it's essentially gas pockets. Like they understand what they're supposed to do should they encounter one. They are registered and certified, and so that gets put on their plate, and so we don't have to deal with that portion of it.
It was one of them, life cycle.
Life cycle, when you are comparing the operations costs, you'll do better off with the geothermal system. If you're just looking at the capital costs, initial initial cost of it, it's not going to look appealing. You need to look at the long-term picture of the whole thing, and considering like the turnaround rates on like the chiller and the maintenance and the chemicals and the water and all those things. But it really depends on who are you building for and how long are you going to hang on to it.
Should we do sector news for those people who have to leave at 9:30 and then I
That's
assume you're.
exactly where I was going.
Yeah, I was
Yep.
gonna say, you're gonna be around to answer further questions.
I can hang around. Yeah, I will mute here.
F-150,
Yeah.
part of the program, but Rob said our Tesla ain't gonna be part of it.
So the number, a number of electric vehicles, including an F-150. I think there's a Kia of some sort and a couple others. Anyway, if anybody in the audience has not driven an electric vehicle yet, I encourage you to do so. I certainly did a fucking drive in Toronto before I bought mine, just to see how much fun they are to drive, let alone anything. Dave.
Last week, we launched our 63.5 ton largest hydrogen fuel cell truck in Edmonton. And so it was on there, we got it launched a week ago. We had a big session, a big event in Edmonton. So very excited about that. 6 years. It starts in the trials on the highway in about a week.
There's a link you could put in the chat, or is there anything that's live that we could?
Yeah, it's called AZETEC, AZETEC. So I can.
Thank you. Anything on? Are you monitoring online, Darko? Okay. Anything on solar? Not anything on bioenergy.
There's considerable discussion about the biogas facility the city is putting in.
Yeah.
And I see it as a possible stranded asset because if you can't use the digestate that comes out of it and spread it on fields, the whole project becomes a stranded asset. The other thing is putting natural gas or gas methane into a leaky pipe system is not a climate win. So I don't think that the full picture is being considered.
certainly on that biodigester system, I've raised the flag of PFAS
Yes.
in municipal waste and, you know,
Pharmaceuticals, heavy metals,
Yeah.
all these things and we would take good green bin waste that makes excellent compost for gardens and contaminating it with all these other things.
yes. Yeah. Anything else on bioenergy? Just I'll make pellets and good wood stove, right? Transportation, about the EV thing, anything else on transportation? We also heard about the
Yeah, does transportation include EVs?
anything on wind?
I hear it's been a bad summer for wind because there haven't been a lot of wind, so again, we gotta look at combos of renewables
So
too, yeah.
so as far as wind turbine efficiency,
Well, not efficiency, there hasn't been a lot of wind this summer,
Right.
so the contribution to the grid is way reduced here versus prior year.
so less wind equals less wind energy. And what's a black eye on renewables for those who want to go there?
Somebody else has a comment.
Education? Anything on collaborations? Anything on anything else that people would like to raise as far as sustainable energy?
Can you hear me?
Wandering online, so we got something
Can you hear me?
with that.
We just have a few questions from the.
Oh, more questions for Natasha.
From the chat.
Okay, let's do, we got 4 minutes left, come on now. Let's do that. I will close my remarks and let Natasha take over. So next meeting is November 1st. We are going to have a presentation by Anchor Concrete and their new Lodestar structures, which is sort of prefab outside building wall construction, and hear about the advantages and benefits of that. It will be a virtual only session. Darko will be posting remotely from somewhere in Africa. So assuming the technology works. So anyway, back to Natasha.
I only am aware of one question really, which is, actually it was answered, but are these the open or closed loops? They're closed loops.
Yeah, we've dealt with closed loops to date. Like I said, if you find an open loop, great, that's amazing. And then just to clarify on the horizontal question and the depth, really, again, at the end of the day, if it's a closed loop, it needs to be balanced. Otherwise, if you put in a horizontal loop and it's not deep enough to really extract from the earth temperature, actually at 4 feet deep, as I'm thinking about it now, you're going to be too impacted by the surface temperature. 4 feet's not nearly deep enough to actually get any of the benefits. So while you can do horizontal loops that do go less deep than a full vertical run, you would need to go deeper than 4 feet. So at that point, just the amount of excavation and trenching that you would need to do, it might just be simpler to go straight down.
Another quick question, actually. Have you ever considered actually selling air conditioning to your neighbors?
No, haven't. I think there's a lot of paperwork involved with doing that. Yeah.
An energy board issue.
Yeah, I'm sure there would be some issues with that. And also especially because air conditioning is the big portion of the electrical load. Then if we're giving more of it elsewhere than our transformer size, the service available, all those things.
Just so you can acquire that heat.
Yeah, I think it's an interesting idea, and I do think as we continue with this and as we're talking about neighbor interaction and interfacing with neighbors, we may have to get creative with how we approach things and how we work with our neighbors. But like I said, to date, we haven't had to deal specifically with that, but we have asked a bunch of questions internally, and even just a question about, like, yes, you own your land and you've got your plot and your survey, but how deep do you actually like own, and when do we start getting into mineral rights and things? And it hasn't come up yet. We haven't had to deal with, but it's questions that we're asking of,
Energy rights.
Yeah.
They don't exist in policy.
yeah, so they're good questions to be aware of, but at this moment, we're just working with what we need to and what we can.
Did your company actually do houses as well as?
No, so I think we affectionately refer to them as the podium special. You'll see I think there's at least 3 or 4 groupings of them in Kingston, the 2 rows of stacked towns, red brick and mansard roofs. There's one on Albert Street, and I think there's one on Mac Street, and there's one somewhere else. So those were like the 20 years ago what Podium was doing, and we're moving on to much bigger things now. Yeah.
One question. Yes, Alan. Helen, can you write down the question, please? Rather than, we have some problem with sound.
Are you speaking to me?
Is Podium only in rentals? Like, does geothermal make sense where it's like condo building, individual owners are paying for their, you know, if you can just put that cost off, those operating costs off onto the owners as opposed to, you know, if you're doing rentals.
Yeah, so Podium is set up just as rentals. That's our focus. If you were doing a condo, you would set it up a little differently. So in a condo situation, you would more than likely not want to front the upfront costs of it. Maybe like $2 million off the bat, just putting it in. Whereas those companies that are willing to finance the cost for you, you may work with them on it and say, okay, great, it's a 0 cost to the builder. Sure, we'll put the geothermal in, but then at the end of the project, they will have to come into a basically like a lease agreement, like when you would rent your hot water tank from Enbridge or something like that. It would be that type of setup between the condo and the service provider. So you can go that route. It doesn't make sense for rentals to do that when there is the ability to back the project with investment capital, but for a condominium, that might make sense. Yeah. Sorry I talked so long.
Have you ever set up a system where you're pulling water from Lake Ontario, using it rather than, I think in downtown Toronto has.
Yeah, they have the district energy system. So we haven't done that so we have a project in Toronto that didn't connect to the district energy system. I think it was a little too far north. So it just installed your conventional like geothermal system. We have another project that might be able to connect. So we'll understand a little bit more about what's available there. But we've never been close enough to the lake to just do it that way. But
Kingston?
I'm gonna say something here because I've heard of a study that was done by somebody who was interested in deep water cooling for Kingston, but they could not find a feasible deep location close enough to Kingston to get those temperature differentials.
Because.
But I haven't seen a study.
We're in the bay sort of thing, not in.
Whereas in Toronto, they take advantage of it. It's quite a deep basin for that.
yeah, I think
But
they
I'd love to see that study.
Maybe that's because it's too shallow going into the river or something.
It's exactly, it's too shallow.
Yeah.
You don't get the temperature
Yeah.
that you need to make.
But do we know who did the study, Paul?
I don't.
How many wells went in at 570?
At 575, we put in 98 wells and they were 400 feet deep. At 485 across the street, I think we put in closer in the range of 60 wells and they went deeper.
8-inch diameter.
8-inch diameter is the drill size, and then the pipe is essentially 2 4-inch pipes together and then grout along it. Yeah.
So when you have the pipes going down, are they insulated from one another? So you're,
No.
essentially the pipes constant temperature for one entire
Yes,
well.
yeah.
And that's why you loop them next well. So
Yes.
you're gonna have a gradient across your field
Yes,
of temperature.
yes. And ultimately, when you get back to they all mix together. So at 575, we had 98 wells that all consolidated into, I think, 18 had
Tanks.
18 it connected in a manifold with 18 ports, and 9 of them were inlets and 9 of them were outlets. And so so basically each one of those 18 connected to a grouping of the 98. And so that's it. But ultimately, when you get into the room, it all just goes into one pipe. So it's constantly mixing and blending, and like the great thing about like a fluid medium like that, it all just swooshes around together and then equilibrates as it goes through. Yeah.
Okay, I think we will shut things down for today. Thank you again, everybody online and in the room. Marvelous talk. And then.
Yeah.
Yeah, no worries whatsoever. Anyway, thank you and look forward to seeing any and all of you in November. Bye for now.
Thank you. Does anybody do great small geothermal?